The third one is actually conservation of linear momentum. Yeah. Vis viva means living force. You looked up the textbook? All right. Vis viva is living force. Okay. So the last one is conservation of linear momentum. So how do you define linear momentum? Anyone? How do you express linear momentum? Mass times velocity. This is linear momentum. You guys cannot just forget it, okay? You keep forgetting everything. What is this? Newton's second law. Rate of change of applied forces, rate of change of momentum. This is linear momentum, mv, okay? So d over dt, mv is equal to constant, okay? Or m times a is constant, or a is constant. Okay. This is not R. Have we proved this? Do you remember proving this? No? When we started, remember we talked about the center of mass, right? Center of mass of two-body system. And then we said the center of mass of two-body system, the acceleration of that is zero. You remember this? How do you define the center of mass? The position of center of mass? You have m1 r1 plus m2 r2, right? Over m1 plus m2. And then we said this is rc, and this we proved as, this double dot was proved as constant, right? That itself is this conservation of linear momentum. Okay. Check your notes. Yes, the center of mass is an inertial point, which means it is moving with, what is an inertial point? Non-accelerating. So non-accelerating means A has to be constant, right? A means this has to be constant. So that means M is obviously constant. So mv is constant. So linear momentum is constant. And why this is 6? This accounts for 6 constants. For a given two-body system, m is constant. You understand? Not space station and the Earth. See, two-body problem, what is the assumptions we made? M1 is really, really big compared to M2. So you have to think about Earth and space station. That would be a two-body problem. See, we can study Even any two bodies has a two-body problem. But if you're talking about relative motion, you have to assume on this platform or on Earth we cannot study, for example, two people as two-body problem. Why? Huh? We cannot do that because Earth has a very huge impact on both the bodies. You cannot ignore that. When we study the two-body, for example, Earth and let's say some orbiting body or moon, what else will have an effect? The sun will have an effect. Every other planet in the solar system will have an effect. But you can kind of say that is negligible. Okay? For studying this, you can say that is negligible. But if you are studying two bodies, you cannot say Earth's effect is negligible, right? If you go really out in space, you can study two people as two-body problem, where the gravitational force is negligible. Or if you go to Lagrange point is you've heard about the James Webb Space Telescope? So James Webb Space Telescope is at a Lagrange point where the gravitational effect of Earth and the moon cancels off. Both of them have a gravitational force, right? It's somewhere in between Earth and moon, because each will have a pulling and a pushing effect, right? So if it's farther away from Earth and moon, yes. So that point will be a Lagrange point. So there you can study two-body problem. It's a point, yes. So if you launch something over there, its relative motion is zero. It stays there. So if you want to focus, for example, the Hubble Space Telescope is orbiting, right? So think about this. If you're orbiting and if you want to keep something focused, you have to constantly rotate, right? Now when you do that, your motion has to be really precise to capture something. Think about if you're capturing something with your camera and if you're constantly moving, you cannot have any other motion other than this, right? You have to keep focusing on that. Now, if you imagine if you send something where you don't have to worry about constantly not stabilizing or not this thing. That is your Kepler's, Lagrange point is such a point, okay? Huh? It's the same as the absolute acceleration, yes. It's absolute acceleration of the center of mass. Absolute acceleration of the center of mass, yes. Center of mass of two-body system. So this is absolute distance of body 1. This is absolute distance of body 2 from a inertial point, right? This is the absolute distance of the center of mass from a so if I do this, nothing changes, okay? Because this is absolute distance, you can just say this is this. And if you take the derivative, it will just be the derivative of these two because M1 and M2 are not changing. And if you take double derivative, then you just did this double derivative. Okay. What else did we do? We did conservation, we did mechanical energy. So we proved Kepler's laws. Which are the Kepler's laws which were proved? Again, why are Kepler's laws laws? Why are Kepler's See, what I'm saying is we proved Kepler's law. Okay? This is Kepler's law. dA over dt is equal to h over 2. This is second law. And orbit equation, remember orbit equation, which says R is equal to h square over mu to 1 over 1 plus e cosine theta. And this is first law, Kepler's first law. Now this is not a law by itself. We arrived at this starting with these two, starting with this. So why do we say it's a law? Even this one we proved that dA by dt is nothing but h over 2. Why do we say it's law? Johannes Kepler was born before Newton. He stated his laws before Newton came up with either this one or this one. Kepler had his three laws in place from observation. Okay, these are the two laws. We'll come to the third law as well, but he did not put it in this. Okay, this is a special. Kepler's law is a special case of this. Kepler purely just said, the first law said planets orbit around the sun in ellipses. That was his first law. But this is, so when you start with Newton, the two-body relative motion problem, you arrive at R, which is trajectory or orbit. So he said ellipses, okay? But what this says is from Newton's laws, you arrive at this and you observe that this represents a conic section, a generic conic section. Okay, and that conic section could be circle, ellipse, parabola, or hyperbola. And E is what defines that conic section. Okay, so Kepler's law, what we observed was we could arrive at Kepler's law using these fundamental laws. So these are much more fundamental to what Kepler said. Okay. Again, we could arrive at this just by using, recall we have arrived at this. Okay? And you should know that we started use one of these to arrive at this. So this is a special case. Okay? So this is a special case. This is just proves Kepler's second law. So what does this say? Can you say this in words? You will be asked to say it in words if you want to be a space engineer. Remember I showed you something on the slides? This just means it's a constant, okay? Equal areas in equal time. So this means the rate of change of it traverses equal areas in equal times. If you have something like this, right, and you have an orbiting body here, we have F. Okay. So let's say this is 1 hour, and this is also 1 hour, okay? The time taken to go from this point to this point. The areas will always be the same, okay? Whatever time it takes, the area covered in that time, it will always be the same. That is what Kepler said, and we proved this. And it only means the right-hand side has the significance that is constant. That's it. Because h is a constant. Okay? Last class we did this. Sorry, did we do this? No. Last class we did energy equation. Okay? We stopped with energy equation or Vis-Viva equation. So what does it say? It says V square over 2 minus mu over R is equal to epsilon, which is a constant. Now, if you look at this, just look at the orbit equation. Orbit equation says this is a conic section. The trajectory R, so you have to think about this like this. Okay, got it? R as a function of, see, I don't want to, nothing else is a function of anything. Theta changes as time changes. R changes as time changes. So R is only a function of theta. This is not vector R, it's scalar R. Okay? So this R is a function of theta. And here, for a given two-body system, if the two-body system is an ellipse, it will always be an ellipse for a Keplerian motion, right? If it's a circle, it will always be a circle. You see that? It doesn't mean for any orbiting body this would be the same. Okay? For a given two-body system, this E will always be the same. You see that, right? This eccentricity will be the same. But what are the kind of orbits we need to discuss? So for circular orbit, your eccentricity is 0. Okay? So this is the first kind of orbit, circular orbit. What is a circular orbit? Can you give me an example of a circular orbit? Huh? All right, let's do it. You'll figure out. You'll understand what I mean by circular. So if you have E is equal to 0, what is your R? R from orbit equation. Everything is geocentric, right? Whatever we talk about. You're talking about geosynchronous orbit. Right. So you have r is equal to h square over mu, right? For e equal to 0. And what do we know about the right hand side? It's a constant. Okay. So for a circular orbit, r is constant. R is not changing. Right? If you think about a geosynchronous orbit, what is a geosynchronous orbit? Its period is the same as the Earth's rotational period. Okay? You can have something in a really low Earth orbit where r is constant. You can have something where r is a constant. But you cannot have, for a geosynchronous orbit, it has to be, the period has to be the same. We'll talk about the period which is Kepler's third law. Okay? 365 pi, 2 pi over 365 should be the period. We'll talk about that later, but it has to be a circular orbit. A geosynchronous orbit has to be a circular orbit. So what is geosynchronous orbit? What is the use of geosynchronous orbit? Anyone? Huh? Yeah. Why would you want a geosynchronous orbit? What is an application? Can you think of an application? Huh?
GPS or communication satellite. A communication satellite where you need to bounce a signal from another place on the Earth, and you can't see it, so you got to have a station in between the two to constantly be at that spot to bounce it from one station on Earth to another station on Earth.
One of the better examples is if you talk about satellite TV. Satellite TV is something, for example, your DirecTV dish is a geosynchronous orbit. It's always there. For this region, it will always be there. Cell phone companies generally don't rely on satellites. There are sat phones which are very different from cell phones. Cell phones. Huh? You need to slow down. Okay. Cell phone companies don't necessarily use this thing. In general, they'll use just a tower. Okay. That's the reason you lose your signal. You get your signal back. But there are sat phones, something called sat phones, and there is something called the Iridium network, which the Iridium network. You have heard about the Iridium? No. Okay. Those are. It's a network of. It is purely meant for sat phones. So you don't have to bounce it off a tower. You can always, as long as you have line of sight, or as long as you're not in a building or anything like that, you can always communicate. Okay.
So what's going on with the
satellite TV has to be there, right? It cannot orbit at different. You're going to get your signal, drop it. Get your signal, drop it. It has to be there. Right? Whatever angular velocity of the Earth is, that has to orbit at the same angular velocity, right? So it has to always be there. It has to be in a geosynchronous orbit. It cannot be in any other orbit other than geosynchronous. You're talking about sat phones or you're talking about cell phones? So satellite TV will have, if you go outside, you may not get that network. Dish network, you may not get it outside. Right. Absolutely. See, since this is constant, okay, what is, remember what is VR? VR is just this R dot, right? Remember? So this is 0, right? Because R is a constant, right? So your V is always just the tangential component for a orbiting body, for a circular orbit. Okay? So your H, we said H is what? Recall, H was defined as R this. Okay. This does not contribute to the so only this component. If you look at the magnitude of this, it is just this. Okay. For a circular orbit, this would just be RV, right? Now, if you have call this 1, R is equal to R square V square over mu, implying V is equal to V circular is equal to mu over. Okay. This is an important, very important result. So please keep this in, you may be asked to arrive at this result. Okay. And so now let's talk about the time period. How do you define the time period? How do you define the time period of a, we'll just complete this and it's not much, just 2 lines, okay? So if you how do you, just 2. So you have, what is the time period? You can say it is circumference over speed. Okay. So this is 2 pi r over v, which is equal to 2 pi r over root of mu over r. Okay. So this T is equal to 2 pi over mu R3 over 2, okay, or T square is equal to 2 pi you see, just pay attention with this one a little bit. So circumference into speed. What is circumference? How do you define the angular speed? The angular speed. See, this is V circular, right? Speed into time is circumference. Do you agree with that? Yeah, speed into time period. Does this make sense? Circumference of speed? Okay. So that is what you have. This is a very important result. This is Kepler's third law. Okay. So the Kepler's third law says the time period, the square of the time is proportional to the cube of the distance. So what it means is, if you have a central body, okay, so let's say this is a elliptical orbit. The average, the time taken for this orbiting body, the square of the time taken would be equal to the cube of the average distance. Okay? So average distance. Here, for a circular body, what happens is, this r is just a constant. So it will just become cube of the distance, cube of the radius. You understand? So what should happen to the period as the r increases? Time period. You understand time period of an orbit? What is time period of an orbit? Right, time taken to complete one orbit. So this time taken to complete one orbit, it increases as the distance increases, and it increases by this relationship. The square of the time period will always be proportional to the cube of the average distance. Okay? Huh? 365 is just a unit. Okay? What we need to know is, see, if you want to send something in a geosynchronous orbit, what do we need to know? This is known. What is this? What is this? Huh? If we want to send something in a geosynchronous orbit, what this? 24 hours. Okay? So convert that to seconds, right? Substitute mu, which is a gravitational parameter. You will get the exact distance, this distance in meters or in kilometers. And there is It has to be that point. It cannot be, although you can fire up and go in and around a little bit, but it has to be pretty precise. This distance has to be pretty precise to get that time period, okay? So now we are talking about, see what happens is, why this is crowded, why the geosynchronous orbit is crowded. You have only a limited window, okay? So if this is your Earth, okay? This window is limited, right? If you're targeting this place. Once you occupy all this, there is nothing you can do to put more satellites in that region. It's done. You cannot go to this point and say we'll somehow figure out a way to reach this. Okay? So that is the reason your geosynchronous orbit is getting crowded. This is a concern, and the low Earth orbit is a concern. Because if something goes wrong here, you cannot even go there and dispose it off because it's really far. It's not lost. It stays there. It stays there as debris. It doesn't go anywhere. It takes years, centuries to even move a little bit from that orbit by itself. So if something goes bad, it's very, very expensive to dispose it off in a geosynchronous orbit. Unless you have, let's say, some energy left to dispose of once it stops working, or once you know you want. Let's just dispose it off. Okay? And this is becoming a concern, the geosynchronous orbit. Huh? I mean, they must have thought about it, but you really need, when anything you need to dispose of you need chemical energy, right? You cannot do this. We don't quite have the technology to do it with renewable energy. What do you need to dispose of? You need thrusters. So what kind of thrusters are you going to use? You're going to probably use chemical thrusters, some gas thrusters, some liquid thrusters. Solar powered, we are not so advanced to figure out electric thrusters. Those are small, those are the small, if you're looking at smaller objects, you can dispose of, but